So I'm Anthony Costa. I'm going to talk to you a little bit about understanding machine intelligence in medicine today. This is the first of a 6-part series that includes topics that are pretty diverse in artificial intelligence in medicine. But to start off, we thought what we would do is to give a fairly high-level introduction and sort of put concepts in the right boxes for people before you start getting into some of the more domain-specific applications of artificial intelligence medicine. As a show of hands, like who here does machine learning research in their actual work? Who here has never really trained a method or run a regression or done anything of that sort whatsoever in their work? Okay, so like 2/3 are in that latter camp. And for the 1/3, I hope that knows quite a bit about this. I hope that we can find something to also discuss. Please feel free to interrupt me during this, and we'll get going. So, what are we here today to do? So, this is a fairly, like I said, it's a fairly high-level talk, and so it's sort of tempting when you look at a title like something like this and think, this talk could go one of a lot of different ways. And so, one way that you could imagine it going is for me to teach you in some way how to develop some new machine learning technique, and then apply it to some kind of medical application, or maybe we don't even get that far. And so this is sort of one approach to thinking about who you are and what you want to do with machine learning in medicine. And here, people who do work in this area, their goal is to improve on the state of the art of the computer science of doing machine learning. So this is the basic science of machine learning. It's heavily based in computational linear algebra and in computer science. And so how do you become an engineer to do this kind of work? Well, first you become a software engineer, and then you get a pretty deep mathematical background, then you go get a PhD in computer science, and then you can come back to a place like Mount Sinai and you can maybe do some domain institution work in the medical space. But more often than that, you're going to go work for Google or Facebook or someone like that. And so this is sort of distinctly not the audience for the talk that we're going to talk about today. And it's important that I make sure that everyone is aware of that, because as we think about the spectrum of the kinds of things that people at Mount Sinai or within a medical institution can affect, we're really not talking about these kinds of people for reasons that I hope will become clear very quickly. Then there's the sort of more applied route to this. So then we have this applying known techniques to solve new problems in medicine. This is not the kinds of work that is done to develop the most basic tools, the basic science of machine learning, or deep learning, we'll get to a little bit later, but is more targeted on taking methods that have been used, fitting them to be able to answer questions about data sets that we would generate at a medical institution like Mount Sinai. And so to do that, you need to understand the data. And that's one of the things that makes medical artificial intelligence and machine learning somewhat unique. And actually the practice of medicine. And we'll get to why that's important in just a little bit. And so this is about deploying and tuning models to be specific to the types of questions that you want to ask within a medical context. So if you're going to, and this is true for like students that join my group and Eric's group, who's a co-author on this presentation, about half of these slides are mine and half are his. Some of you know him. This is the sort of applied route. And the applied route, you don't have to go get a PhD in CS, but there's still some basic requirements that you kind of need to know in order to be effective in this area. So a good understanding of computer systems and architecture certainly helps. You're going to be running these things on computing systems. It might be in the cloud, it might be on premises, it might be all sorts of other places. Having competence and not getting stuck with the tools is really important. Competent software practices, not really the level of a Google software engineer or something like that, but certainly competent software practices. And then a whole bunch of other kinds of specific tool training, et cetera. So, for those of you who are working in this area, everyone knows CS231 from Stanford, sort of the canonical machine intelligence course that everyone takes. And you're going to need to know some tool-specific stuff, the tools that you're interested in using. A lot of skills in data science, you can actually analyze what you're working on. But then also this medical practitioner kind of route for applying AI requires some domain knowledge. or if you don't have the domain knowledge, you're at least going to get it through pretty extensive interactions with clinicians that are going to drive the questions that you're going to ask. So we have super technical people on one hand who might not work at a place like Mount Sinai. Domain scientists who are applying things here, which are maybe the most technical people who work at a place like this on machine learning problems in medicine. And there's one group of people that are completely left out so far of everything that I've said, and of course that is the clinicians or the physician scientists. So going from technical to applied sort of progressively through here. And these clinicians and physician scientists often get left out of this conversation, or very often feel that they're left out of this conversation, which sets up its own interesting problems with how we deploy these technologies, and I hope we'll get there later. But clinician involvement is super important. In fact, I would argue that there's almost no problem worth doing without having a clinician or physician scientist involved to begin with, because they do the most important thing. They basically define the hypothesis generation and define the tool that you're going to eventually want to deploy. Presumably you want to actually affect patient care or outcomes or some process involved in the practice of medicine, and you need physicians to be a part of that conversation. So those are ensuring that the problems being addressed are valid, important, driven by an actual need, deployable, actionable, meaning you can actually make this work in a clinical environment. And so in addition to what I do for the AI group here, I'm the director of this biodesign program, and actually this kind of needs finding thing is something we've talked a lot about, both in the context of previous iterations of this workshop series and the hackathon and Sinai Innovations and a whole bunch of things that that happen here. This basic needs finding process is the thing that clinicians and physician scientists that you work with can be deeply involved in and help you guide the development of your technology. So why do we need them? And what do the physician scientists need? And I think the most successful projects that we've ever worked on, certainly the most successful that I've ever seen, that have made it to the point of actually impacting patient care, are physicians that are intimately involved in the problem discovery process. So I'll talk about that in just a second. But I think most important beyond this is to commit themselves to ongoing engagement with the technical and data science teams that are actually working on this. I was recently at a meeting this last week and was really impressed by the number of people who came up who were all core deep learning engineers, but when they described the teams that work with them, every single one of them stood up and said, and here's the physician that's working with us that goes to our group meetings every single week. And I think that goes both ways. In our group, we have a lot of people who can implement these methods, but they go to rounds in the morning, right? And they go and they actually engage on the playing field of the physician, and we sort of expect people to do the same in the reverse direction. So this is basically a biodesign process. This is a needs finding process, and this is the same thing that you would go through. I mean, I don't know if anyone is planning on participating in the hackathon in October, but this kind of needs finding process is something that you want to, even if you kind of already know where you're going, it's something that you want to do. And we have a group at Mount Sinai called Biodesign, which I'm the director of, which is this needs-driven kind of process for innovation in medicine. So what is that? I'm not really going to talk about biodesign. There's 2 slides here. But basically, you want to define the problem in a way that gives you some kind of clinical validity. And generally, we do that with 2 things: the development of a need statement and then input into that need statement. So development of a need statement is something like a way to address problem, define your problem, in some population that gives you some outcome. And as input to that, you go through and you actually understand a whole bunch of things that drive the answers to those questions, and those include disease state fundamentals, existing solutions, and then some things that are relevant to whether or not you're actually going to be able to deploy this within a clinical environment. All of these things, each one of these individual things, is best done through sort of intimate exchanges with the clinicians that would ultimately be using your technology. So that's why we frame this kind of needs-driven process within the context of a physician that's really driving the question, because ultimately that's who's going to put it into practice. So all that is to say something quite defensible, that is clinical involvement is crucial. It's my belief that, like I said, the most successful teams are ones where clinicians are deeply engaged with data science teams, and certainly vice versa. Okay. If you don't do that, you you get solutions that are technically spectacular and clinically irrelevant. This is the one that I use. It's maybe a little bit unfair because it's kind of like, it's been beaten to death at this point. But the original Chest X814 paper out of Stanford said a lot of things, but a lot of the things it said about its performance on chest X-ray diagnostic diagnosis really didn't conform to how the underlying disease states were diagnosed in a real clinical environment. In fact, it had very little to do with it. Generally, for example, pneumonia is not diagnosed solely based on a chest X-ray. There's a whole host of other information, and a lot of this was glossed over and not really thought about in the context of how you would employ something like this that would actually augment the workflow of a radiologist or whoever would be interested in this process. So it's a very famous example, although there are plenty of others. So we end up on this continuum of from technical to clinical, and I put these books up just because everyone knows them. If you work in deep learning or statistical learning or machine learning at all, you probably know both of these books. Deep learning is relatively recent. I guess it was 2016 now, so it's a few years old. And then sort of the classic statistical learning books, which are quite technical. And people, this is Jeff Dean from Google, and then every single one of these people is someone who has worked with us within the AI Sinai group on a project that spanned from the more technical to the more clinician-driven. And over here, I have this deep medicine book from Eric Topol, who, if you don't know, you should probably follow on Twitter, or at least get to know a little bit. It's worth reading the book as well. He kind of has the zeitgeist, I suppose, in artificial intelligence in medicine right now, if you are engaged in social media or AI technologies these days. It's becoming easier and easier to stay on top of some of these things and get some broader perspectives. There was a great Nature Medicine entire series this year with a whole bunch of stuff, including one from the same author of that book, Eric Topol, that I said before. But it's getting to the point where people are, really starting to put together, practical aspects of how we deploy artificial intelligence technologies and really take it very seriously in a very practical way. And these Nature Medicine reviews I certainly recommend. And these slides, I'll find some way to make available or put them on our website or something like that for everyone. I'm not sure if there's a mechanism through the workshop, but we'll figure out how to do that. Okay. So we're going to go through a whole bunch of applications, but some of these you probably heard of, others of which you might not have thought of before. But I just want to spend a little bit of time talking about what's been successful, what's been published, what's been translated, what's been FDA cleared, just to give you a sense of where the impact seems to be now, both on the academic side and in practice. So if we take a 100,000-foot view of the current impacts of AI in medicine and some of its limitations, I think a lot of these are pretty intuitive to most people, right? Imaging is the sort of is the standard test or the standard thing that most of us think about, or a lot of us think about. It's been perhaps the most successful and the most significant in terms of clinical deployments for AI in medicine, especially in radiology and pathology. So rapid, accurate image interpretation, classification, segmentation, all the kinds of things that we do in images that I'll talk about just briefly in a little bit, including workflow, reducing medical errors, enabling patient data ownership. These are the things that some of those articles that I mentioned before identify as the 100,000-foot view of where AI is going to have an impact in the next 5 to 10 years. I think limitations are also somewhat, I guess, obvious to many people. We think a lot about data privacy in medicine, and of course, privacy is a major issue and limitation in the way that we train models, the way that we gather data, the way that we share models, the way that we share data. Security goes hand in hand with that. Bias, we're actually going to talk about a little bit in the way that we collect data, what that means for how our tools generalize, what that means for whether or not we can take our method that we've trained on some data, understand how it's going to work, we move it to another institution, another site, another application. So there's a huge array of things here, and we're certainly not going to go through all of them. I'm going to talk about a couple of things that we've done in our group that are specifically related to imaging, but I want to make sure that that we at least touch on these others. So, in summing up a lot of these kinds of this whole set of possible applications, I think the thing that most of the community has really settled on as a way to describe how AI is going to be deployed or is being deployed in the clinic is the idea of augmentation. 5 years ago, we were talking a lot about people losing their jobs, and as it turns out, I don't believe that. I don't think the community believes that anymore, and we really started to use this word augmentation as the way that we describe how AI is deployed in the clinic. And I think that can be summed up in a few different ways. Everyone has their own interpretation of it, but common ways that this is described is to free doctors to be doctors again, as opposed to spending time dealing with a lot of minutia, to spend their time on more complex types of cases or more complex issues, where an AI tool can give you a lot of benefit, but not necessarily into those very unique situations. And the Topol crew who talk about augmentation in medicine also talk about this human-centered care. So removing a lot of the minutia, burnout, record keeping, et cetera, so that the relationship is really just between the doctor and the patient. Now, actual implementation of this and not letting us slide into something that is just continuing to use AI to increase the workload on physicians is something that we actually have to take very seriously. It's well beyond the scope of this talk. But doing this successfully requires the entire community, really the entire field, to make a real centered effort toward making sure we just don't slide down and burden people by leveraging these things to make them able to move through more cases as opposed to deal with more complex ones, as an example. Okay, so a lot of things that people do you've probably seen lots of headlines like this, especially if you don't work in the field or if you don't do any machine learning research. The favorite headline that people like to write is that this artificial intelligence tool beats doctors at X. Right? And that's a great headline. It generally has not that much to do with reality, but nonetheless, comparing AI technologies with the performance of physicians in some kind of restricted clinical trial, use the term clinical trial quite loosely, is an important goal because it gives us a benchmark. Right? And so in imaging, this is a set of imaging peer-reviewed stuff. I was pretty happy that our paper actually ended up at the top of this list from this review of Nature Medicine. But nonetheless, radiology, neurology, all of the imaging-based domains have been extensively researched and have been published on. This is like a tiny, tiny little list. Those of you who pay attention to this field know that there are hundreds of papers published every single day in the archive and other places, and so this is really just at the top. But radiology, pathology, dermatology, ophthalmology have all had fairly successful applications built and compared against the performance of physicians. There are also a fair number of works specifically related to clinical outcome prediction. So these are things like in-hospital mortality, sepsis risk, suicide risk, delirium risk, mortality, all sorts of in-hospital and clinical outcome prediction, prediction of readmission, et cetera. There have been a growing number of, and we're not going to talk about the regulatory aspects of this very much at all, but there have been a growing number of approved FDA AI tools. And I guess the first one was Artis, very famously, in 2017. You can see there's just a couple in 2017, a great number in 2018, and this is just a list from the most recent paper I could find that was a review. And there are many through there. The FDA process for AI technologies in medicine is moving forward, but we have a long way to go to maximize the value of the technologies within our regulatory frameworks. So there are other challenges related to deploying these things and to taking all of these fantastic studies and turning them into tools that can actually be deployed. And I think there are a few that really stick out to me. One is that the amount of true prospective real-world validity that we've been able to establish with many of these tools is not high. Even in that list of all of the compared to physician statements, well, many of those are not prospective control trials, and they haven't really been established to have any validity. We did a simulated trial in our study that happens to be on that list, but it wasn't, even that was not a true prospective control trial. Our regulatory framework is somewhat out of date. These things are changing. There are programs being initiated in the FDA. Most famously, I can't remember the exact name of it, but the Trusted program that, for example, Apple and other software makers are leveraging to deploy things like what we're on your wrist these days. And then the pace of technical progress is also really extraordinary, and it's very hard to keep up with everything that's going on. And to some extent, this induces our thought process on the regulatory framework, because how do you really treat something that moves this quickly? Really, our regulatory framework is not designed to deal with that very well. Okay. So how do you keep up? Up until about a year ago, I actually went through every headline of the archive cs.cv, cs.ii. If you know what that is, great. If you don't, it's a place where you can throw papers. There are hundreds a day that are relevant to medical computer vision and other types of medical applications. It gets completely absurd, to say nothing of actually reading the standard peer-reviewed journals. So I stopped doing that, and I tried to find ways where I could get social media's machine learning technologies to feed me the right things in the right order. I'm not sure that I've done a particularly good job of it, but it seems to be working for now. This is just my advice. Find technical and clinical domain experts on social media. This is not hard. If you follow none right now, just follow Eric Topol, and you'll find a lot of things that he says that you'll be able to find other people to pay attention to him seriously, and so on and so forth. Honestly, subscribing to Reddit machine learning, there's a lot of interesting discussion that happens both there and in its stuff on Twitter. Subscribe to appropriate newsletters. This is relatively new. I love this one called Dr. Penguin. It's only in its 9th week, I think, right now, but it's spectacular. It gives you the top 5 or 10 articles that they've looked at. They actually go through and do a high-level summary. So for those people who aren't necessarily practitioners in the art, you can read and understand this, and if you are, you can force them to go to the paper. It really takes the burden off of you to read every single thing that comes out every week, which gets very difficult. Medium, sort of. There's high quality and low quality stuff on things like Medium. There's many others other than Medium, but just an example. And here's what I say: don't do. Don't try to read every single paper that comes out every day, because it's all you'll end up doing. Okay. So that was a 20-minute introduction. We started a little late. Some thoughts on people and opportunities in machine learning medicine. But since most people here don't do any machine learning research, the rest of this talk, what I wanted to do was, like I said at the very beginning, put some terminology and some applications in the right boxes so that you can, when you approach a problem that you happen to know something about or want to solve, you can speak a little bit of the language with the people who are going to do the work, as well as understand what kinds of tools are most appropriate for solving that. And so this is just kind of fun. What machine learning is not throwing a bunch of data into a machine and just out-popping an answer, right? There's a lot more to it than that. But I thought we would start with an example that everyone knows, or at least most of you probably know, which is literally a linear regression. And think about that as a machine learning problem, because ultimately a linear regressor is a machine learning classifier, well, it's not a classifier, but whatever. It is a machine learning tool. It just happens to be a particularly simple one. And then upscaling that into tools that are dramatically more complicated, to first order is not difficult to conceptualize, and so I'll try to do that for you. And if something gets confusing in here, please just let me know, raise your hand and ask. So, okay, machine learning broken into 12 steps. This is taken and sort of distilled both by myself and Eric, 2 authors of this presentation, over the course of a couple of years. It starts with sort of engineering best practices in machine learning systems and uses this very simple linear regression task as an example of how you step through this on a simple basis. Okay. So what is machine learning? Machine learning is algorithmically finding patterns in your data so we can correctly react to new data. That is, you're going to train some model that's going to predict, given X, what is the answer to some other covariable. So in general, what we're concerned is whether or not the next piece of data that comes into our model is accurately predicted. So the example that we're going to use here is something completely, I'm not sure that anyone would actually want to do this, but we're going to use it as an example. Right? What we're going to do is we're going to build a artificial intelligence technology into an EMR that's going to take all sorts of data that is commonly collected during an exam and predict the length of that patient's kidney, because we've decided that for some reason this is important. Now, I have no idea if this is important. My guess is that it's not at all important, but that doesn't matter, right? Our question that we defined is, based on the data that we nominally have about a patient during an ordinary exam, tell me, to the best that you can, what the length of their kidney is. The leading dimension of the length of their kidney. Okay. So, predicting kidney length. That's our objective. Now, I already sort of told you a little bit about the data that we have access to, but even if you just think through this, you want to do this for EMR records, right? So you're going to have access to certain things. So you have some EMR, you have some person here. That's our input. And so from this EMR data, we have access to a whole bunch of things that might have relevance to kidney length. Some of them might be free text notes, right? This may or may not be true, but certainly, free text notes associated with a visit to your primary care doctor may contain clues about something going on with your health, right? So if you're significantly overweight, maybe believe that weight is going to be related to kidney length, and so that would be a strong predictor of kidney length. Maybe that's going to be in the note. But the easier thing to do is just, because we have annotated data in a fixed field with a fixed format, weight, we can just pull that and use that as our input. So we have complicated types of data in our EMR. Free text, where we need natural language processing techniques to build models and to figure out what it's actually saying. We also have very simple structured data like weight, height, things that intuitively make sense to us that are going to be predictive of kidney length in a patient. I think probably to everyone that makes some degree of sense. I say here domain expertise helps, but it doesn't take a well-trained clinician to believe that this might be true. So we're going to take all of our data and we're going to split it into some number of sets. We're going to use some amount of data to train our model. In this case, it's just a linear regression. So given a height of 100, given a height of 6 feet, what is the most likely kidney length? Then we're going to split that up. So this is a particular example. This doesn't have to be exactly right, but maybe we take that and we split half of that data into training sets. Into the training set, build a quarter of that into a validation set, and a quarter of that into a test set. The important thing here is the training set and the test set being fully held out. So this is your perspective data, that what you're trying to do is to build a model on data that you've seen, and then use the held out data to look at whether or not your model generalizes to unseen data. There's a whole bunch of other stuff that we're going to talk about eventually with how that really works, but that's the general idea. Right? So we hide away some data that we're only going to look at periodically. That's the validation set. We're going to ignore that for the purpose of the discussion, especially in the context of linear regressor. And we're only going to look at this when we're done. This is this test set to see how we generalize to the next patient. Okay, this I think is often overlooked issue, and that is exploring your data in some way. So if I, for example, collect a whole bunch of information about the height of patients at Mount Sinai, I look at, say, 1,000 examples, and I look, and that data is normally distributed, so across, let's say, males or females, something like that. That makes a lot of sense, right? We expect things to generally be, central limit theorem says we're eventually going to get to normal distributions in a lot of these independent variables, and so we expect things to be normally distributed. If I then look at my data and it has some very crazy distribution, like, it has a super long tail, or it's really centered with short people, but I don't have any tall people in my data set, all of that's going to be red flags, right? Something has gone wrong in my data collection process, and ultimately the model that I'm going to train is going to be biased in some kind of way that is going to limit the generalizability of the tool. So you plot kidney length. Let's say we have a bunch of actual radiological measurements of kidney length and height. So we plot kidney length as a function of height, and we get something that looks linear-ish. And then we plot the distribution of kidney length and height, and they're reasonably normally distributed. And that's about as complicated as we need to get for a simple example like this. The data conforms to our expectations about what our population looks like. And then the next thing to do is to choose a tool. Okay? And tools, there are lots of different types of tools. In this case, we're going to try a linear regressor because we believe that to be the true relationship of the data to the input that we have access to. In this case, we're just doing weight or height. Okay? Obviously, this choice gets very complicated very quickly as the types of data that you're looking at gets more complicated. On imaging data sets, we don't do linear regression. We do something else. So we're going to talk about that briefly. We come up with some objective function that we want to minimize. In this case, this is the mean squared error. Think about this as linear least squares in a linear fitter. This is restating something that I've said before. Generally not okay not to know the intricacies of the algorithms themselves. Even, a linear regression. I bet a lot of people in this room have used linear regression before and not really known the intimate details of how that is arrived at, what the optimization technique underlying in the Excel formula that you wrote or in MATLAB or whatever you did. That's generally fine. What's generally not okay is to not understand the data you're working with, which is exactly what this whole exploration of data that I talked about beforehand is aimed at. Find patterns. Okay. So we start and we train our model. We look at the results that we have, and we decide whether or not the model that we're using is appropriate for the data set itself. In general, we can sort of sum this up saying don't use more model than you need. And this is actually intuitive. There are these words that we use: complexity, overfitting, and bias. If we're using more model than is necessary. And what that means is basically this. What is the true distribution of your data? And is your model under appropriately or overfitting that data? Okay. So if the true answer is something in here, you know enough about your data to know that it has this form, whatever that happens to be, and you fit a linear model to that data, you're underfitting the data, right? In another case here, example of a model that is massively overfitting the data and is not going to generalize very well. The next data point that you get, presumably in the true model, is going to be here, and this is going to massively miss the prediction of y given x in that particular data point. In our case, again, relatively straightforward. We're pretty sure it's linear related to height or weight. Tune this. You can do lots of fancy things with the more and more complex types of models, but in the linear regression, it's a relatively straightforward optimization process. We validate it, see how our model is performing. If it's not performing well, go back and tune something, try it again. And eventually, test the model on our held out data set. So this is weight versus average kidney length. Here's our linear fit for the labeled data that we have access to. And then we went to the test data and we looked at something about our error. So we computed some kind of error statistic and looked at how well we did that. You're all probably familiar with R squared for a linear model. That's okay for here. In deep learning models, we use other things, but that's perfectly fine for here, and it tells you something about how related your data is to the fit that you come up with. Then here's the most ridiculous thing on this entire presentation is that I jump from 10 to 11, which is from test to deploy. Realistically, deploying this model, even a simple linear regression within the context of a complicated EMR at a hospital system, is not something you just turn a key to do. That takes a massive amount of time and effort and regulatory considerations and practical considerations and IT considerations and all sorts of things that mean that in general, to get this into EMR systems, it's going to require moving this out into a company, and they're going to have to do all of that before you can move it back in. Now, obviously at Mount Sinai, we have some teams, there are data science teams that do work directly with the EMR. Something like this is probably implementable, but it's still just not a turnkey kind of thing. So going from test to deploy is a big leap, right? There's a lot of stuff that happens in between there. And then lastly, monitor, maintain. Let's see something happens to your patient population, right? let's say that over the course of the last 60 years, Americans have in general gotten more and more overweight. This happens to be true. So if I never looked at any data for overweight Americans in my original data set, if I trained this in 1950, do I really believe this is going to do a good job of predicting kidney length with a data set that has moved, right, in my input space and in the underlying patient characteristics and population? This is what that is going to do. So we started a little late. I was really only supposed to do a 40-minute talk. I'm going to go through a few things very quickly here on sort of classification approaches. And I'm going to skip the kinds of things that we've done for the most part in our group. But I wanted to talk a little bit about a few things that we've done that are sort of conform to this needs-driven approach and try to identify where in those steps that we've just gone through in a very simple machine learning model, a deep learning model fits. Okay. In general, we talk about machine learning in sort of four main subfields, and really there's only two that we're going to discuss here. Supervised learning is what we just basically talked about. You have a bunch of data, you have a bunch of labels. The labels tell you something about the data that you want to predict from some new unseen data set. So here's a label of an image and it says dog, and here's a label of an image that says bicycle. This is a strongly supervised data set of something. Okay, unsupervised machine learning. This is most classically and most well known clustering and dimensionality reduction, where you're trying to find some kind of metric that gives you an opportunity to cluster or to build groups of data that are similar in some way. So a bunch of pictures of dogs look similar to us humans. We need to find a way to teach machines to actually cluster those images together. They're all like dogs, similarly like bikes. It's this and this. So clustering dimensionality reduction seem to be our well-known techniques here. Supervised learning is beyond the scope of this talk, where you have partial label data and use that to derive labels for unlabeled or unseen labels. And reinforcement learning, which is well beyond the scope of this talk, which is perhaps one of the most well-developed areas of machine learning, up until very recently had relatively little application in medicine. That's changing dramatically right now, but it is an active research topic. So what about deep learning, right? So we've trained a linear classifier, and I've called that machine learning because it takes some input and gives you a prediction based on a supervised data set of height, weight, or kidney length. What does deep learning do that's different than that? Well, deep learning is this subset of machine learning. And let me tell you a little, the single and most salient thing about deep learning that differentiates itself from machine learning. In our machine learning example, we had a bunch of strongly supervised, annotated, structured data, right? So we looked at our data set and we said, these are the features that are relevant to the question that I'm answering. So in this case, I used height, I used weight, built a model for both of those in a linear classifier. That was what I did, right? I used my knowledge of the domain to, and this is, I'm going to use a term that you should remember, engineer the features such that they predicted the labels of the outcomes that we're interested in. So this feature engineering is inherent to all machine learning technologies or machine learning techniques. In this case, we did that process manually. And up until 15 years ago, a lot of supervised learning was done with manual feature engineering. And in fact, a lot of machine learning today is still done with manual feature engineering. Instead, though, in a data set like this, and we're all familiar with basically deep learning as it applies to imaging data sets and taking an image and saying that this image is of class A, B, or C, or to in the image localize an object. If you pay attention to really anything that's happening outside of medicine right now, you search for cat on Google and it returns a lot of pictures of cats. That's not because these images were specifically labeled. It's some technology that is able to classify that image as a cat. And I don't know about you, but I don't know how to write down an expression that says that this is a picture of a dog, right? There are some features in here. There's all sorts of stuff happening in our brains when we look at that picture that say that's a picture of a dog, but I have absolutely no idea how to teach a computer to look at that and say that's a dog. Right? So I have no idea what features of this image, mathematically, have any correspondence to this being a true dog image. Right? Similarly, I don't actually, this seems ridiculous, right? There's a binary classifier. I'm just going to go dog or not dog. I'm going to do Silicon Valley. The hot dog detector is an example of a binary classifier here. So this is a picture of a not dog. I don't know how to tell a computer that this is not a picture of a dog by some feature like, if it's blue, if it's majority blue, it's not a dog. That's actually not a terrible idea, but that's not generally going to generalize very well. If I painted this dog blue, it would still be obvious as a dog to me right here, but my classifier based on that sort of engineered feature would obviously fail. So what are these features? Okay. I have labels, but we have no idea what to write down in terms of features. This is what deep learning does well. Deep learning is a whole mess of linear algebra. We're not going to get into the details of network structure or anything like that. We have nowhere near the time for that. It automates the process of feature engineering. However, in doing so, it very often obscures the features themselves. So it can be very difficult to tell within a deep learning model what it is about the image that the machine thinks is characteristic of a dog. So this is the so-called problem of explainability in deep neural networks. But in general, these deep neural networks, in this particular class of them, we're talking about convolutional neural networks, can learn feature maps that progressively get from low order to higher and higher order features to classify, for example, in this case, we're talking about a face classifier. So these feature representations are what deep neural networks are really good at, and this is that process of engineering features automatically in a deep neural network. So we're going to run out of time to go through a lot of the things that I would love to go through, but there are some basic tasks that we're generally concerned with in imaging, and that we're generally concerned with in imaging as applied to radiology, pathology, etc. And generally, these are not distinct from those that are interesting to most tech companies that are not working on image processing. Classification, meaning that I happen to know this is a cat. Classification and localization, this is where the cat is. Object detection, many objects in a single image, so many tumors in a single brain scan. Instant segmentation, which is some degree of locality that goes beyond bounding boxes. And fully semantic segmentation, where you're labeling every single picture of the image with some information about what that pixel represents. There's lots of data sets available to sort of play with this as you build your models. They're called sort of the canonical data sets in the field. And I'm going to skip over the details of these things in the context of convolutional networks, other than to say that there are techniques that we use to sort of take an image and build a representation or a lens on that data that makes it useful for feature extraction by the deep neural network. And in imaging, we call these convolutional layers, and they're very successful in this field, and has led really to the explosion of image processing as deep learning applied to. We did something in our group related to classification of emergent events in CT head scans, motivated by the fact that hemorrhage is this, obviously, super hemorrhage is a devastating disease, and is obviously very time sensitive in terms of intervention, and so improving the time to diagnosis is quite valuable. So, for example, you have a dural or something, or an ischemic event over here, we want to detect those, and we want to separate those out from ones that maybe are a tumor, right? And they don't necessarily have to be treated right now. We built a really big data set to do this, and we actually built a mechanism by which trained radiologists and people who are not deep learning practitioners, but the people who actually have the domain knowledge that are able to provide labels to our images, were able to take radiology reports and build a annotated, structured data set associated with each one of these images. And we use that to eventually train a convolutional neural network, skipping over a lot of details here, to classify critical events from non-critical events based on the labels that were generated from that annotation of the radiology report. And what we did was took that and used emergent or non-emergent classifications to reprioritize the work queue associated with the radiology work queue. And then in a simulated prospective trial, this was not actually implemented, showed a reduction in the time to diagnosis by prioritizing those scans of the deep neural network with subhuman performance moved to the front of the line. So what I like about this particular example, and the reason that I give it in the context of a talk like this, is because what we didn't do was say, we're going to beat radiologists in detecting emergent events when somebody comes in and has symptoms of a stroke and goes for a CT head. What we said was, we know something about the way that medicine works, and we can insert this abstraction layer that's going to make the existing workflow work better. Right? And so we built a classifier that doesn't do as good as a human, but yet still yields a net benefit to time to diagnosis for these patients. And so this is why my argument, this is the best example I can come up with our own work, why that really deep clinician engagement is so important, because without them, you can't figure out how to do this, right? You can't define the problem well, you can't define the deployment mechanism well, you really can't define how this is going to work in clinical practice unless you have that clinician on your team who's constantly guiding you in the direction that's going to yield something. So this is literally a classifier that isn't as good as humans, still got it in Nature Medicine, because this is the way that problem was approached. Okay, a couple of last things before we end. I want to leave just a few minutes for questions, and I'm happy to stay longer. I don't have anything. A couple of disclaimers on medical data sets. When you're at Google, or you're at Facebook, or you're at any of these companies that traffic in data, acquiring data to train machine learning models is a relatively straightforward task, right? Or at least it's not a major effort, right? It might be technically difficult, but it's all the data is there. You just have to figure out how to grab it. Okay? In our case, in medicine, that's not necessarily true. In fact, it's exclusively not true. And we have a lot of things that your Facebooks and Googles don't have that are roadblocks between us and the data. You can argue that maybe they should have those roadblocks, but that's a whole different conversation. So we have privacy issues. We have a fairly unique bureaucracy associated with the practice of medicine. We have the expense of the generation of medical data. And we have a scarcity of MD domain expertise. That's not to say there aren't a lot of doctors here, but the amount of work that goes into, for example, labeling a data set requires highly trained, fairly expensive people, and that's a huge bottleneck in the process of generating data sets that are relevant. We're also pretty siloed in medicine, right? It's generally very difficult to share data between institutions, which can induce some interesting effects on the way that the tools that we build generalize from institution to institution. So we're kind of lucky in our group to be actually embedded in a clinical institution. That's a good thing. Everything about how we have the opportunity to build data sets that have value and then learn on them is made better by being inside the institution and working with clinicians. The downside to that, of course, is that it's relatively difficult to recruit the kinds of really awesome machine learning talent to come into an institution like this. And this is something that the institution cares a lot about right now and is really working on. I think we'll be successful. Another way of saying medical data is expensive is that medical data costs lives, right? This is not my anecdote. This is Eric's. But you can wish for more data, and if it's for a particular disease state, but what you're saying, of course, is that you're hoping more people have that disease, right? Which is not exactly a nice feeling. It really isn't what we should be thinking about. And keeping in mind that this is patient data that comes from real patients with real pathologies or diseases, something to keep in mind, and also contributes to the expense. And this is also just kind of worth, to your question earlier, what we're talking about in terms of the expense of this kind of data. You upload a cat picture to Facebook, it costs you nothing, it costs Facebook nothing to store, and they get to train on it. In our case, we get a new MRI data set for a patient, that probably costs the institution $3,000. Labeling it, let's say it costs $75 to label it, that would be really cheap, but let's say it's possible. And let's do that 100,000 times, and all of a sudden that's a $300 million data set, right? At the same scale that Facebook would throw, that's pennies for Facebook for cat images. It's $300 million for us at the scale that's relevant for training a three-dimensional MR classifier, for example. So that's kind of the end of what I wanted to say. I'm sorry we started a little bit late, but I'm happy to stay and take any questions. There's a whole bunch of people that contribute to this. This is in no way, shape, or form an exhaustive list. I ran out of time this morning to update these slides. But Eric and I work a lot together. There's a whole team in neurologic surgery. There's a whole team in radiology. A whole bunch of people in orthopedics, radiation oncology that work with it. work with us. We have grants outside the institution, both extramurals and a number of industry partners. We work pretty extensively with the TIMI group, and we have a number of really excellent students who have worked with us over the past few years and continue to work with us now that have done a lot of the work. So thanks very much for your time. I hope this was helpful, and I'll be happy to take any questions.